Uniqueness of prime factorization. Welcome, everyone. Today, we are going to dive into a very important concept in number theory, the uniqueness of prime factorization. Now, to start off, let's look back at what we covered in our previous lesson. We learned that any composite number, which is basically any number that isn't prime, can be broken down into a product of prime numbers. You've already practiced this using factor trees and division. However, there is a much more profound part of the Fundamental Theorem of Arithmetic that we need to discuss today. It isn't just about the fact that a number can be broken down into primes. It's about the fact that this factorization is unique. Now, when we use the word unique in mathematics, we mean that there is one, and only one, possible set of prime factors for any given composite number. There are no other hidden primes out there that could replace them. Now, don't get confused if you see someone writing the numbers in a different order. While you are free to change the order in which you multiply these primes together, the actual prime numbers themselves, and the specific number of times each prime appears in the product, will always remain exactly the same. In the next few slides, I'll show you exactly what I mean by this using some practical examples. Understanding the concept of uniqueness. Now that we've introduced the idea that every composite number has a unique set of prime factors, let's look at what uniqueness actually looks like in practice. To illustrate this, imagine two different students are both given the same task, to find the prime factors of the number 60. First, let's look at student A. This student decides to start their process by dividing by the smallest prime, which is 2. They see that 60 equals 2 times 30. Then, they continue breaking down 30, finding that it equals 2 times 15. Finally, they break 15 down into 3 times 5. So, student A's final result is 2 times 2 times 3 times 5. Now, let's look at a different approach taken by student B. This student chooses to start by dividing by 5. They see that 60 equals 5 times 12. From there, they divide 12 by 2 to get 6, and then divide 6 by 2 to get 3. Following this path, student B's result is 5 times 2 times 2 times 3. If you compare the two results, you'll notice something very important. Even though the students followed completely different mathematical paths and used different starting points, they both arrived at the exact same set of prime factors. Specifically, 2 2s, 1 3, and 1 5. The only difference between their answers is simply the order in which the factors are listed. This perfectly demonstrates the concept we are studying. The prime factors themselves are fixed and unique, regardless of the method you use to find them. Real-world analogy. Now, to help you really grasp why this concept of uniqueness is so important, let's step away from the numbers for a moment and look at a real-world analogy. You can think of prime factorization as the DNA or a unique fingerprint of a number. Just as every human being has a unique DNA sequence that identifies them and distinguishes them from everyone else, every composite number has its own unique set of prime factors that identifies it. This means that no two different composite numbers will ever share the exact same prime factorization. This brings us to our next point. Since this fingerprint is so specific, mathematicians use a standardized way of writing it down to avoid any confusion, which we will look at in the next slide. Standardizing the notation. To avoid any confusion caused by the different orders we might encounter, mathematicians use a standardized way of writing prime factorizations. This ensures that everyone, everywhere, is looking at the same mathematical sentence. The rule is quite simple. We always write the primes in ascending order, which just means from the smallest value to the largest. To show this formally, if we have a composite number, let's call it x. We represent it as x equals p sub 1, p sub 2, all the way up to p sub n. In this notation, p sub 1, p sub 2, and so on up to p sub n represent our prime numbers. And to be very precise, we arrange them such that p sub 1 is less than or equal to p sub 2, and so on until we reach p sub n. Finally, as you'll see in our upcoming examples with much larger numbers, when a prime factor repeats, we don't want to write it out over and over again. Instead, we use exponents to make the expression much more concise and easier to read. Now that we've seen how different paths can lead to the same set of prime factors, you might be wondering, if the order can change, how do we keep things organized? Detailed example: factorizing $32,760. Now that we have understood the theory behind uniqueness and the idea of prime factors acting like a number's DNA, let's put this into practice. We are going to move away from small numbers like 60 and apply this concept to a much larger number to see how we can systematically derive and standardize its factorization. First, we begin with step 1, where our goal is to divide by the smallest prime factor, which is 2, as many times as possible. We start with 32,760 divided by 2, which gives us 16,380. We can divide by 2 again, resulting in 8,190. One more time, dividing 8,190 by 2 leaves us with 4,095. Now, notice that 4,095 is an odd number, so we can no longer use 2. This means we must move on to the next prime number. Moving to step 2, we look for the next smallest prime factor, which is 3. We divide 4,095 by 3 to get 1,365. If we try to divide 1,365 by 3 again, we find it is no longer divisible, so we proceed to the next prime. In step 3, we move to the next smallest prime factor, which is 5. Dividing 455 by 5 gives us 91. Next, in step 4, we check the next prime, which is 7. When we divide 91 by 7, we are left with 13. Finally, in step 5, we reach our last prime factor, which is 13. Dividing 13 by 13 leaves us with 1. Once we reach 1, our division process is complete. Now, in the next slide, I will show you how to take all these individual pieces we just found and organize them into the proper, standardized notation we discussed earlier. Organizing and notating factors. In step 6, we take those raw factors we just found and organize them in ascending order, which simply means from the smallest value to the largest. Looking at our list, the prime factors we identified are 2, 2, 2, 3, 3, 5, 7, and 13. Next, in step 7, we move to writing this in standard exponential notation, which is the professional way mathematicians present their results. Instead of writing out the same number multiple times, we use exponents to keep it concise. So, instead of writing 2, 2, and 2, we write 2 to the power of 3. Similarly, for our 2 3s, we write 3 to the power of 2. This gives us our final polished expression. 32,760 equals 2 to the power of 3, multiplied by 3 to the power of 2, multiplied by 5, multiplied by 7, multiplied by 13. It is important to remember that regardless of whether you used a factor tree or the repeated division method we just practiced, you will always arrive at this exact same result for the number 32,760. Now that we have successfully broken down that large number, 32,760, into its individual prime components, we need to tidy everything up. This brings us to our next slide, where we will discuss some common pitfalls to watch out for when performing these calculations. Common mistakes to avoid. First, let's talk about the error of including composite numbers. A very common mistake is to stop the factorization process too early. For instance, you might write 60 equals 2 times 2 times 15. While that multiplication is correct, it is not a prime factorization because 15 is a composite number, not a prime. You must continue your work until every single factor is prime, so the correct final form should be 60 equals 2 times 2 times 3 times 5. Second, be careful about ignoring the order. Now, mathematically speaking, 5 times 3 times 2 times 2 is exactly the same value as 2 times 2 times 3 times 5. However, as we discussed in the previous slide regarding standard notation, it is not in standard form. To keep your work professional and consistent, always arrange your primes in ascending order, from the smallest to the largest. Finally, watch out for calculation errors, especially when dealing with large numbers. When you are working with something as complex as 32,760, like we saw in our detailed example, it is very easy to make a small division error. To avoid this, I highly recommend a quick check. Once you have finished your factorization, multiply all your final prime factors back together. If they don't equal your original number, you'll know immediately that you need to recheck your steps. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even when you understand the concept of uniqueness, it is very easy to make small mistakes that can lead to incorrect answers. Once you've mastered these points, you'll be ready to review our key takeaways in the final slide. Key takeaways. First, remember the concept of uniqueness. As we discussed with our DNA analogy earlier, every composite number has exactly one unique set of prime factors. There is no ambiguity here. The fingerprint of the number is fixed. Second, keep in mind the principle of order independence. As we saw in the example with student A and student B factorizing the number 60, the path you take or the order in which you divide doesn't matter. Whether you start with the smallest prime or the largest, you will always arrive at the same collection of prime numbers. Third, to keep our work professional and easy to read, we always use standard form. To maintain consistency and avoid the confusion we mentioned in our common mistakes slide, we always write our prime factorizations in ascending order. This means we arrange the primes such that p sub 1 is less than or equal to p sub 2, and so on, all the way up to p sub n. Finally, let's not forget about efficient notation. When you encounter repeated factors, as we saw in our large-scale example with 32,760, don't write them all out manually. Use exponents to represent repeated prime factors. For instance, instead of writing 2 times 2 times 2, simply write 2 to the power of 3. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session on the uniqueness of prime factorization to ensure everything is clear. If you have mastered these 4 points, you have a solid grasp of the fundamental theorem of arithmetic. Great job today.